Hello class, welcome to our lesson today dealing with section 16.5. So you want to make sure you're in chapter 16 for today's lesson. It deals with what's known as scientific notation. Now, based upon the wording of what's given here, scientific notation is typically used in the science realm. So let's go ahead and get started with what scientific notation is talking about. Scientific notation by definition is writing a product of two things. So one of them is a factor, so this factor here in green. This factor has to be greater than or equal to 1 but less than 10. So essentially like a single digit in front of the decimal point, and anything after could be a decimal. And then it's times 10 to some power. Notice that the factor here is between 1 and 10 essentially, okay, less than 10. But the powers are the second part always 10 to some power. It's going to be 10 to an integer. Notice it doesn't have to be a whole number. It doesn't have to be positive. It could be negative. But it's not going to be 10 raised to like a decimal like 2.3 or a fraction of like 3 over 10. It's always going to be raised to an integer power. And so that's the setup for scientific notation. Other things can look kind of like scientific notation, but by definition, scientific notation has to fit these two descriptions. So if we want to determine if something is scientific notation, we look at two things. First off, is this number between 1 and 10? Essentially, yes, because it's 4 in a decimal place, and the pieces after the decimal point, times 10 to an integer, looks good. This one over here, 0.84, is not correct scientific notation because it's not greater than 1 or equal to 1. So this is not correct scientific notation. The next one, 42.1, boom, automatic, not scientific notation because 42 is greater than 10. The last one, 9.12, that's in good shape. Times 10 to the negative 8, the fact that it's negative is okay as long as that's an integer. So that one is okay as well. Okay, we're going to go through kind of a lot of detail on this first slide, but once we get through this first slide, we should notice some shortcuts. So one way to solve these questions is this is in scientific notation given to you. It has the number times 10 to a power. If you want to write the number in what's known as standard form, that's rewriting it in a way that looks like a normal number that you're used to seeing. So one way to do this is to say, okay, well 6.12 is 6.12. Then times 10 to the first, 10 to the first is 10. So you just multiply those two things together, and you get 61.2. The next one, 5.8 times 10 to the second. Well, 5.8 times 10 to the second, which is 100. So 5.8 times 100 would equal 580. The next one would be 8.5 times 10 to the 0. Now, we've dealt with this sporadically throughout the semester. Remember that anything raised to the 0 power is 1. So 10 to the 0 is 1. So 8.5 times 1 would still be 8.5. The goal here is that we shouldn't have to do this multiplication every time. The nice thing about these questions is the fact that it's 10 to the first. Notice where the decimal point moved. 6.12 becomes 61.2. The decimal moved one spot to the right for the standard form. The next one, 5.8, it moved 2 spots to the right because you're multiplying by 10 to the second. This last one, 8.5, didn't move at all, so it's still 8.5, so it moves 0 spots. So instead of having to do the middle step every time, it should be initial setup, write that down, equals the answer, and I think it'll make more sense on the next few slides. Here's 4.01 times 10 to the third. Well, that's times the 1,000 because it's 10 times 10 times 10. Or each time you multiply by 10, it moves the decimal one spot to the next place value. So 1.04, then move the decimal 1, 2, 3 spots. If there's no number there, you just add a 0 in. Notice I didn't add 3 zeros to the end of the number. I moved 3 place values for that number. The next one, I'm going to move 5 place values to the right. 1, 2, 3, 4, 5. And I end up with 720,000. Now remember, those two things are the same thing. So 7.2 times 10 to the fifth and 720,000, those match up perfectly, and they're the same number, just one's in scientific notation, one's in standard form. The next one, you have to move 8 spots. So 3 of those spots, 1, 2, 3, and then 5 more zeros would get you this number. Scientific notation is more helpful on big numbers like this last one. Science tends to use a lot of big and small numbers, so that's why scientific notation kind of comes into play. Let's go ahead and look at the next group of questions and see if we can figure out a pattern. The next one is the same, but it's a negative exponent. Now, one thing that students try to do here is just say, oh, it's the same thing, but just make it negative. Well, remember that Everything in mathematics is about whatever it is and its inverse or kind of an opposite idea. So if 4.01 times 10 to the third moved the decimal 3 spots to the right, 4.01 times 10 to the negative third should move it 3 spots the other direction or to the left, because it's just doing the opposite of whatever it was doing before. So if I do that, I just move it 3 spots to the left, and it should become a very small decimal type number, which makes sense because you're getting things and dividing by 10 essentially, instead of multiplying by 10. You'll deal more with that multiplying, dividing idea when you talk about negative exponents in the future. The next one, times 10 to the negative fifth, you're going to move the decimal back 5 spots. The last one really shows where scientific notation becomes helpful. This is pretty easy to see and to understand, but when you had to move the decimal back 8 spots, this is really hard to read. Okay, so there's like 7 zeros and then the 2, 1, 8, 7. This is a really, really small number, but scientific notation can allow you to show something that's that small in a kind of a more compact situation. So, the rule of thumb is if the exponent is positive, then you move the decimal point to the right because you're multiplying by 10. If the exponent is negative, you move the decimal point to the left, and that's because you're dividing by 10. The next question talks about density of water, and anything that has a higher density will sink, and everything that has a smaller density will float. So the density of water is 1 times 10 to the third. Now, one option for these questions is you could just move the decimal 3 spots over here, 3 spots for the brick, but only 2 spots for the apple, and then compare them. But if things are already in scientific notation, you might find it easier to just compare their factor pieces at the beginning and their powers of 10 on the second half. For example, this is definitely 1 times 10 to the third. Well, look at this brick. Brick is also 10 to the third, so they're at least close. They're in the same ballpark. But notice 1.84 is higher than this, which means the brick is more dense, which means it will sink. Now, we probably could have guessed that if you've ever tried to have a brick float in the water. The apple, though, even though it has 6.41, it's only times 10 to the second. So it's only going to move 2 places to the right instead of 3. So like this brick would be 1,840 when I move it 3 spots. This apple's only 641. And notice it's times 10 to the second. Anything with 10 to the second is less than the 10 to the third, even if this is just 1. So this will float, the apple will float, which would be the idea of like bobbing for apples, for example. It will float because it's less dense. So the easiest way to compare numbers is first look at their powers of 10. Less exponent, that's a smaller number. If they have the same exponent for the power of 10, then you look at their kind of first factor number, and whichever one is higher or lower will dictate what you need. You don't want to be changing them all to just standard form all the time. You can do that. It'll just take you a little bit longer. One other thing I'd like you to try is on whatever calculator that you use, try multiplying 25 million times 38 million. Whatever calculator you use when you plug that in, please try that. You'll probably get some strange number. It'll either look like this. It'll say 9.5 times 10 to the 14th. Or your calculator may show 9.5e14. This is just scientific notation. You've probably noticed this when you multiply numbers over and over, that eventually it starts to do this weird thing with powers. Or it looks like a decimal and all of a sudden the number got smaller. It didn't really get smaller. It just made it into scientific notation. So this would be 9.5 and then move the decimal point from that, 14 spots to the right. The e to the 14 is just a different way of writing it that some older styles of calculators use because they don't have the ability to pixelate times 10 to the 14th. So you might see this e14, which just means 9.5 times 10 to the 14th. It's the exact same thing. It's just written in a slightly different way for your calculator. If you're using a phone calculator and kind of turn it sideways, that might also be able to do the trick on some of those things, depending on the situation. But make sure whatever calculator that you're using for your math class, you understand what scientific notation is looking at and what it means. Okay, your homework today, 6 through 24, 27, 29, and 31 through 35. The first group of questions are similar to like these ones. Please write the original setup and then equals the answer. Okay, original setup, write the scientific notation, then equals the standard form answer. That's kind of the first group of all the questions. When you get to some of the later ones, like 29 and 31, they require some multiplication. So you may have to change things into standard form and then multiply by a decimal or a percentage. Please use a calculator on 29 and 31. Show the setup still, and then plug that in and find your final answer. Have a good day, everyone.